In this tutorial, we will expand on our previous example where we were calculating the variation and the standard deviation, and we will calculate the standard error of the data set, which is the error around the mean of all means, as well as the confidence interval, specifically the 95% confidence interval. And then I'm going to show you how to create box and whisker plots. Now, in this data set, this is the first time where we are going to subset a normal distribution. What do I mean by that? Well, in this example, I was looking at koala masses across urban and suburban data populations, and thinking that maybe koalas were heavier in urban populations rather than suburban populations because maybe they ate more junk food. Well, if I look at the total distribution of koalas versus the sub-distribution of only the urban koalas, and then only the sub-distribution of suburban, and actually, given my hypothesis, these should have been reversed. Well, let's do that. Let's do that right now. Looking at this would be the suburban, and this would be the urban. Urban would be more massive. You can see that we have subdivided our total data set into two smaller data sets. And each one of these smaller data sets also has a mean and also has a variation. And then the larger data set has its own mean and its own variation. And so what I'm asking you to do in this example is to calculate the grand total mean and variation, and the within distribution means and variations. Let's go ahead and do that. Erase all this. To calculate our mean for our entire data set, it's simply equal to average of our entire data set. Not the geometric mean, we're leaving that behind us. So just the average of our entire data set, C2 to C101. Let's go down here and calculate the mean for only our urban data. Average. And now we're not going to select all of this, but we're only going to select, oops, I'm going too far. Only our urban data. Can't do this. There we go. And in my data sheet, it's C2 to C51. And let's do that again for our suburban data. Average. And the suburban data starts in C52. And we go to C101. There we have our mean data for our suburban. And you can see that the mean suburban mass is less than the urban mass. Well, now we can go ahead and calculate our variation. And as you recall, to calculate our variation, which is the average sum of squares, we need to first calculate sum of square, or the square differences. So what we're going to do is first calculate the square difference for the total data set, which is this right here. To do that, we have our entire data set mean. So we can say equals 34.5 minus the grand mean, which is 29.0. And don't forget to square it because we're squaring these differences. Once again, 34.0 minus the mean, the grand mean, squared. Let's go ahead and just draw that down, but of course we have to lock our mean. If we drag that down, then we can easily calculate the variation, which is equal to the sum of all of those data points divided by, now remember we're calculating the average square difference, but we're not using 100, which is the total number of data points. We're using 100 minus 1. And there's our variation. The standard deviation is equal to the square root of that variation. And the standard error of the mean, which is the mean of all means, and you have to watch the lecture to understand what that means, is equal to the standard deviation divided by the square root of the total number of replicates, which in this case is 100. If you weren't sure, we could just do count and then select all of the data points. It will be 100. And we get 0.4456, blah, blah, blah. The confidence interval, the 95% confidence interval, is where the data is likely to fall if we were to do this again and again and again, or where the mean is likely to fall. And the confidence interval is equal to plus or minus 1.96 times the standard error. Or you can abbreviate that to 2, whichever one you want to do. I'm going to use 1.96. So the confidence interval is equal to the standard error times 1.96. So we say that the data is very likely to fall within 0.0 or plus or minus 0.87 of 29.0. So 0.87 units plus or minus the mean. Now, the next set, the urban data, we figured out what this mean was right here, and we want to figure out what the spread is right here. So we need to calculate the variation. Now, it would be tempting to use these square differences, but these square differences are more specifically the square difference of the points with the grand mean. And that's not what we want. We want the square difference of the points with the urban mean right here. So to do that, we need another squared difference column, but in this column, we're going to call that within subsets. In this squared difference column, and let's put another column in here just to give us a little bit of space, within the square difference within subsets, we're only going to do it for the urban data for right now, is equal to the mass data minus not the grand mean, but the urban mean squared. And we'll do that again and again and again for all of the urban data points. So what we have to do is lock that urban mean, and we'll drag this down. Oops, too far. Just for the urban data. We're not going to do it for the suburban data because that's going to have a different mean. Now we can calculate the variation for the urban data, which is equal to the sum of all of these data points. There's 50 of these data points. So we divide that by 50 minus 1, or 49. The standard deviation is equal to the square root of that variation. The standard error is equal to the standard deviation divided by the square root of the number of replicates, which is 50. And the confidence interval is equal to 1.96 times the standard error. Now we can do this for the suburban data. And let's go ahead and do this in this column over here. We calculate the mean, the square difference between the data point, which is right here, 27.4, minus the suburban data mean, which is 25.1, and of course we have to square it. Now we're going to do that for all of the suburban data points, so we have to lock H22 in my data sheet, and we drag that down. Now we have the square differences for all of the suburban data points. So we can calculate our variation as the sum of all of those data points divided by, as before, there's 50 data points, so 50 minus 1. The standard deviation is equal to the square root of the variation. Standard error is equal to the standard deviation divided by the square root of the number of replicates, which is 50. And the confidence interval is equal to the standard error times 1.96, or you can round to 2. This is so important, and you will be doing this again and again and again when we go over analyses of variance. But for the time being, the next thing that I want to show you is how to create box and whisker plots. Now, box and whisker plots are a great way to show you the spread of data. It gives you a sense of the average, it gives you a sense of where the data fall around that average, and it gives you a sense of where outliers exist. To do this, Excel has very easy functions. You can calculate or create a box and whisker plot for all of the koala mass data by simply selecting all of the koala mass data and going to Insert, and then where the histogram button is, just go click on that and select box and whisker. And this is a box and whisker plot for all of the data. And what we can see is this line right here is our average. These lines right here are our 75 and 25th quartile. And these lines right here are our 10th and 90th decile, where approximately you have 10% of the data fall below this line, and 90% of the data and then 10% of the data fall above this line. So about 80% of the data is right in here. Let's go ahead and do this for our suburban and our urban data sets. And the way that we can do that is by selecting only the urban data, inserting a box and whisker plot, and then right-click on this and say Select Data. Let's edit this series to say Urban, and then we'll add a series here. We'll call this Suburban, and our series values will only be the suburban data points. My mistake, I added a parentheses where I shouldn't. Click OK, and there you have a box and whisker plot for our koala mass for urban and suburban. And you can see that the urban data has a greater mean and a greater mean than the suburban data. It's also possible for you to see where the variation is. Essentially, if we were to lay our histogram on its side, how fat is that histogram? How wide is that histogram? Okay. Now, just to give you a sense for how Excel is calculating all of that stuff, pretty easy. We can calculate that through easy functions of percentile. The 10th decile is equal to percentile of our urban data, which is C2 to C51. And then you have to tell Excel, well, what is the percentile? In this case, it's 0.10. The 25th quartile, percentile, C2 to C51, 0.25. The median, we could just type in median, C2 to C51, and we get 33.4, or you could also type in percentile, C2 to C51, 0.50, and you're going to get the same number. The 75th quartile is equal to percentile, C2 to C51, and 0.75. And the 90th decile is percentile, C2 to C51, 0.90. And these are the values that Excel uses to create that box and whisker plot. Our mean is right here. This is our 75th and 25th, so 25th and 75th. And then the box and whiskers, this is our 90th, and this is our 10th. And you can prove this to yourself by looking at these values on the box and whisker plots that we just created. Let's go ahead and repeat this for our suburban data. The 10th decile for the suburban data is equal to C52 to C101, 0.10. I believe that's right. Let me check. Yes, that's correct. Our 25th quartile is equal to percentile C52 to C101, 0.25. Our median, again, we could type in median C52 to C101, or we could type in equals percentile C52 to C101, 0.50, and we should get the same number. Our 75th quartile is equal to percentile C52 to C101, 0.75, and our 90th is equal to percentile C52 to C101, 0.90. And there you have how we can easily figure out the values for a box and whisker plot.